Commercial building HVAC doesn't mean you have to sacrifice efficiency, carbon impact, or comfort. Utilizing heat pipe HVAC solutions and innovative pump-assisted systems in commercial buildings, ACT can help you reach your corporate carbon emission reduction goals. Drastically cut energy cost and carbon output in small and multi-level buildings in all types of climate conditions. Traditional glycol runaround systems have a lot of issues. This system will have lower heat transfer capacities and higher parasitic pumping loads. In addition, routine maintenance is required. There is a much better approach to energy recovery that eliminates these setbacks and delivers tremendous benefits to commercial building HVAC called pump-assisted split-loop thermosiphon. Looking at the top section of this high-rise building, we see the top floor control for the HVAC system. This, along with the lower floor control system, pumps air throughout the building. Cold outside air enters the HVAC system and travels through the ACT Energy Recovery preheating condenser coil, where the air is tempered by transferring the building's warm exhaust air via the evaporator coil. This preheating of the incoming air reduces the energy output needed from the main air handler's heating coil, providing a more efficient heating system. The warm building exhaust air travels through the return duct system from the lower floors of the building. It is directed to the ACT Energy Recovery exhaust coil, which in turn recovers the exiting sensible heat and transfers it back through the system via copper transfer lines and returns it to the Energy Recovery preheating condenser. The heat transfer is accomplished by fractional horsepower circulating pumps. The copper energy recovery transfer line orientations are optimized during the design phase of the project. Depending on layout, some installations have upper and lower transfer lines. We simplified this video example for clarity. In the summer season, hot outside air enters the HVAC system and travels through the ACT Energy Recovery pre-cooling coil, now the evaporator, where the air is cooled prior to the air handler's chilled water cooling coil. This pre-cooled air greatly reduces the tons of cooling required. The air-conditioned air then flows through the ventilation system down through multiple floors of the building. The pre-cooling coil once again uses the building's return air exhaust stream. In the summer season, the exhaust energy recovery coil is now the condenser coil, and the cooler refrigerant pumped to the other side of the building to pre-cool the incoming air entering the air handling system. The makeup air that is heated or cooled depending upon the season flows to each lower floor and gets a final temperature and airflow adjustment from the variable air volume boxes. Utilizing ACT's refrigerant pump-based systems allow energy recovery transfer of the incoming and exhaust air streams up to 300 feet apart. The heart of the ACT pumped energy recovery system is a series of variable speed fractional horsepower pumps that are tied to a PLC controller. Under certain climate conditions, refrigerant is required to maintain optimum heat transfer performance. The controller regulates flow rate based on the refrigerant level of each heat transfer line. The level is monitored by analog level sensors, providing variable level feedback to the controller. The controller increases or decreases pump speed to maintain proper levels of refrigerant for optimum heat transfer. The utilization of flow and level controls is a major breakthrough, as previous refrigerant-based systems were unable to operate properly. System fluid level transducers monitor refrigerant levels and provide feedback to the PLC controller to increase or decrease refrigerant flow. This avoids potential dryout conditions in the heat transfer lines based on climate conditions. The application discussed in this video was installed in Chicago. The system size is 21,500 cubic feet per minute at approximately 600 feet per minute. The resulting payback analysis yielded a 2.1-year payback period, which included the cost of installation. The system will produce an annual utility savings of $101,484. An additional benefit was helping the building management team meet their carbon reduction goals. This system annually saves over 735,000 kilowatts and 72.1 metric tons of carbon reduction. Contact us today to find out how utilizing heat pipe heat exchanger technology can reduce your carbon footprint.